Hello my dudes, and welcome back to Viewfinder Engineering. Today, we're going to be talking about block diagram algebra. So first things first, I'm the realist. We need to understand what each piece of this pretty little picture means. Now, there are three basic shapes: circles, squares, and lines. Circles denote addition or subtraction, squares represent multiplications, and lines represent variables. Let's take a look. So let's say we're feeding an x into this box and we want to get a y out. Whatever is in this box isn't really important right now. I mean, it's going to be a transfer function, but we'll get to that later. And similarly, let's say that we want to add, a and b and get c. Well, we can do so because lines are variables, and they're probably better denoted as x of s, y of s, a of s, b of s, and c of s, because lines are variables in the Laplace domain. We can feed our lines into squares and into circles and get out different lines. So this x variable is transformed into a y variable. This a and this b combine to get to a c. And a, b, and c is what we're going to look at first. So let's go talk about circles. So circles take our variables and they add or subtract them. They're used to show feedback in loops, but also can help denote disturbances or sensor noise, anything unexpected that's being added to the system can also be accommodated by a circle. And this picture is not quite complete yet, because the other key thing to know about circles is that we have to include pluses and minuses to denote what we're doing with each variable when we feed them into a circle. So for this case, where they're both pluses, a plus b equals c. But let's take a different case where this is a plus and this is a minus. So in this second case, it's a minus b equals c. So our first example of a practical application of a circle would be in like a negative feedback loop. So in this system, we're using our circle to denote like controller error. Our r is our reference velocity, our x is our desired velocity, and our e is the error between the two that's getting fed into the controller. Since we have a plus and a minus here, we know that this circle is going to be governed by the law r minus x equals e. And this makes sense within the context of our controllers. If you'll remember, our control law is made up from a controller constant times our error, which is the difference between the output we want and the output we have. So everything checks out, negative feedback, 10 out of 10. So the other situation in which we might need to incorporate circles are for cases like disturbances. Disturbances are anything that's affecting the system that we didn't initially take into account. So whether it be like your car is going up a hill, or your car is hitting a rock, or your car is hitting the rock. A disturbance is just anything that we didn't account for that needs to be added into the system. And you will see that we're denoting it with two pluses because now we're adding. So in this case, our equation for our circle is f plus d equals u. So before we can talk big picture, we first need to circle, get it, back around to our buddy the square. We already sort of established when we talked about lines that squares get us from one variable to another, but there's a few more key points we need to cover. So first off, we need to talk about what's inside the square. Squares represent transfer functions, and the transfer function inside the square can be any number of things. This can be our controller, this can be our system plant, this could be a transfer function that takes us from the system output to the sensor feedback that goes back into the controller. You know, the possibilities are endless, the world is your oyster, but transfer functions. The next key point to hit on here is that our squares multiply, and they don't just multiply from one variable to the next, they also can be multiplied together. So this can be simplified down to just one square that takes us straight from x of s to z of s. So thanks to our handy-dandy friends Algebra and the Laplace domain, we can see here that our y of s's will cancel out, which means we can go straight from x to z. This concept can be especially helpful when we're finding our closed loop transfer functions and our open loop transfer functions, which reminds me, it's big picture time. When designing controls, closed loop transfer functions and open loop transfer functions become important. And what better tool to help us get to those than our handy-dandy block diagram algebra? First, some definitions. The open loop transfer function takes us from our error to our output. The key point here is that it does not take into account the input to our system. So in this case, it would just be from E to X. It does include our controller law and our system plant, but no sensor feedback, no input, just this piece here. Now the closed loop transfer function does include our system input. It takes us from R to X, you know, all of this, the whole shebang. And the best way we can describe this is the forward path over 1 plus the loop transmission. What is that, you ask? Good question. The forward path is our stuff on top, and then our loop transmission will be taking us all the way around the circle. So, putting this formula in action, our forward path will be k of s times g of s. And we will divide this by 1 plus a loop transmission, which taking us all the way around the loop will be k of s times g of s times h of s. Now, the important thing to note about both of these equations is that they are transfer functions. And if you'll recall, transfer functions are single output, single input. They are linear, time invariant. So, if we had a disturbance or some sensor noise anywhere in the system, we wouldn't be able to find our closed and open loop transfer functions. Let's say we have a disturbance up in here like we showed at the beginning of this video. We now can no longer use our block diagram in this form to find our closed and open loop transfer functions. What we can do is get rid of this and find our equations of the system in terms of our input R, and then get rid of this and find our solution in terms of our disturbance D. And thanks to the principle of superposition, our outputs based on R and based on D will be able to add. But for basic controller design and all of that stuff, It's just going to be one output, one input. So I just want to finish up by reiterating the point that our closed and open loop transfer functions are super important. When we get into controller design, especially with like root locus and coefficient matching and stuff, it's going to be extremely important that you understand these, but you also understand them in terms of the bigger picture of block diagram algebra. But that's another topic for another time. Thank you all so much for watching. If you liked this video, be sure to give it a big thumbs up, especially if it helped. And be sure to subscribe for more college level math and engineering and science and all that jazz. I will see you in the next one. Bye!